Hello viewers, and welcome to this TI.com training. I am Philip Dolo of the DLP Pico projection team, and today we're going to be discussing how to use one of our smallest chipsets currently available to create affordable, flexible, smart home and industrial displays. The 0.2 nHD digital micromirror device is the feature of the DLP LightCrafter 2000 evaluation module, or EVM. This EVM, which you can see here, provides an open-ended interface compatible with most embedded host processors such as the BeagleBone Black or the Raspberry Pi. Today we will learn how you can use this functionality to kickstart an embedded systems project employing DLP technology. Since the 0.2 nHD chipset features a number of moving parts, let's break them down. We'll start by talking about how the chipset itself fits in a full embedded system in a short system overview. This will help you get a better idea of how the different components in the 0.2 nHD chipset contribute to the full package. With this understanding, we will then examine an example of how to interface the 0.2 nHD EVM with a host processor. For this training, we will use the BeagleBone Black, but keep in mind that any host processor with the necessary interfacing capabilities will do just fine. Finally, we will talk about much valued design resources that you could potentially use in your project. Once your embedded projector is working, you will want an application to exercise it after all. The 0.2 nHD, or DLP 2000, comes in an affordable package, but don't let that fool you into thinking it isn't packed with functionality. Rather, this chipset maintains a small 0.2-inch form factor, which is measured across the diagonal, with a high brightness and contrast that is synonymous with the DLP brand. The power consumption of the system is as low as 180 milliwatts, so you can be sure that your embedded device will stay connected. Of course, a long-lasting embedded device like this one wouldn't be valuable if it couldn't also listen to your favorite embedded host processor, which has the software libraries you need to get things done. The system produces a 640 by 360 native display resolution, so you won't need to sacrifice image quality in your project. The value proposition of the DLP 2000 chipset makes it well suited for smart home applications. Examples of this include smart heads-up displays, embedded user interfaces, and even smart assistants, such as in the kitchen. The use of DLP technology for these kinds of embedded systems provides strong differentiation due to the freedom and flexibility DLP provides in these spaces. Since the system display is no longer tethered to a small TFT display, the developer can get more creative with how information is displayed, what is displayed, and where it's displayed. When transitioning from a standard embedded display to a DLP projector, the interactivity provided by touchscreens does not need to be sacrificed. A multitude of substitutes, such as those seen here, can allow a DLP-based embedded system to interface with the user. Structured light interfaces, for example, will use deflections of projected light captured by a camera to be computed and translated to user input. Meanwhile, time-of-flight sensors can be installed on an embedded system to detect a user's hand interfering with the travel of acoustic or electromagnetic waves. Picking the right technology will go a long way to giving users a premium experience, so check out our Smart Home Applications white paper to help you decide what implementation suits your project best. We've talked about the DLP 2000 chipset, so let's also touch on the 0.2 nHD EVM, which accompanies it. The DLP 2000 chipset, which powers the 0.2 nHD EVM, achieves around 20 lumens of brightness in a credit card-sized form factor. The EVM itself is really part of a full TI design, which contains a design guide and design files in addition to the hardware itself. The reason for this is, from an engineering perspective, to provide an easier path to making use of the system as a template for a serious design project. The design files featured in this TI design provide the schematics, bill of materials, and layout files that you need to create a new spin of the board based on your vision. That way, if your embedded system project matures, you'll be able to respin the board into a design just the way you like it. You may have noticed by this point that the 0.2 nHD chipset contains more than just one component. In fact, it contains three. These are the DLPC 2607, the DLPA 1000, and the DLP 2000, which carries the show. The 2607, serving as the controller for the chipset, receives video input from you, the user, and converts it into control signals that can drive the DLP 2000. The DLP 2000 is the digital micro mirror device, or DMD, which bounces incoming RGB LED light out into the outside world based on instructions from the 2607. Of course, none of this would be possible without the DLPA 1000, which functions as a power management IC driving the LEDs in tune with the 2607 and providing power to the whole system. There are a couple of important components in the 0.2 nHD EVM which aren't directly tied to the DLP 2000 chipset itself. A flash memory tied to the 2607 controller is used to store object code and splash images and is read by the 2607 at startup. As such, code updates provided by TI could be programmed to the flash memory if needed. A projector on, or proj on, logic circuit is the power switch of the system. An external proj on control is routed to the host processor GPIO lines for your convenience. Finally, an EEPROM chip living on the I2C bus is used as a device ID so that the host processor, such as the BeagleBone Black, knows to load the appropriate drivers on boot. In addition to the EEPROM, the I2C bus also serves as the primary means for the host processor to give 2607 commands outside of the standard video interface. Resolution, video format, brightness, and other options can be modified over I2C. Now that we better understand what is in the DLP 2000 chipset and the accompanying EVM, let's talk about how to make use of them in an example system implementation. The DLP DLCR 2000 EVM, or the DLP 2000 EVM for short, has a user's guide which contains some basic how-to information, so it's worth downloading as a reference. Once you have the EVM, you should also get your hands on a power supply compatible with it. The system expects a 5V 3A limited supply, so an equivalent power source would suffice. You will also need a BeagleBone Black or an equivalent host processor should your preferences differ, and the means to talk to your host processor. For this demonstration, you will need a micro SD card large enough to hold the Debian distro we will use. With the BeagleBone Black, a Debian distro with support for the DLP 2000 EVM will be necessary. Links to compatible images can be found on beagleboard.org. A compatible image will come with the Cape overlay driver for the DLP 2000 EVM preloaded in the system, but you could choose to load the Cape overlay yourself if you decide to use a custom distro with specialized software. Links on how to do this will be provided in the final part of this training. There are a variety of ways to load the operating system to the BeagleBone Black. On Windows, I've had success using SD Formatter and Win32 Disk Imager, links for which are provided here. For Linux and Mac users out there, this step can be skipped, since the SD card can be formatted to suit the BeagleBone Black without additional software. When powering the system standalone without a host processor, the EVM will boot to a splash screen resembling the colorful marquee below. However, we want to run some software with this board, so we will need to hook up the host processor to do so. After powering both the EVM and the BeagleBone Black on a freshly installed Debian distro, the default credentials should work to log into a remote SSH session. If you're starting from scratch, now would be a good time to tell the system to download whatever software packages you may need for your project. I recommend downloading MPlayer 2, which is a simple video player that can be used in Python demo scripts provided with the EVM, as well as for general purpose use. As we discussed earlier in this training, the DLP 2000 EVM uses I2C as a primary means to receive commands from a host processor. Simple I2C tool commands are built into this Debian release, so we will use that for now. The DLP 2607 operates using 32-bit I2C registers, so we will need to send our commands in the format seen above. In the example, we have first switched the EVM to display external video by sending hex 00 to address hex 0b. A number of video input sources are supported in this chipset, such as splash screen and test pattern generator as well. Once we have done this, we will then tell the EVM to set the display to native 640 by 360 resolution by sending hex 1b to address hex 0c. If the system has been set up successfully up to this point, you will be greeted by an image of the BeagleBone desktop on the output of the DLP 2000 EVM optical engine. In order to help you take your development further, we have provided basic Python scripts in a BeagleBone repository that simulates various basic chipset behaviors. Some of these include brightness adjustment, test patterns, and system status readings. If the BeagleBone Black isn't your platform of choice, you can still download these scripts by looking to the GitHub repository referenced below. Combining this with use of the DLP 2607 Programmer's Guide is a great way to learn the system inside and out. The DLP 2607 Programmer's Guide contains a very thorough list of I2C commands that you can use with the system. Some functions, such as LED brightness adjustment, require the use of compound I2C commands, which require a number of steps to execute properly. To get the most out of your EVM, I highly recommend learning from these examples to help you get started on the right foot. The fishbowl demo is pretty prominent in some of our DLP 2000 promotional content. If you want to check the video out in action for yourself, you can do so using the video test script provided in the DLP 2000 Python library. You'll need to have installed mPlayer 2 and set up the EVM as the primary display for X11. Once you've done this, you can execute the given Python script or even play the video back yourself using a suitable video player to watch the fish swimming around firsthand. Keep in mind that since we are using DLP projection technology, black levels can be used to simulate totally freeform displays. This gives the fishbowl video the impression of a circular rather than rectangular screen. Before we conclude, here are some useful resources to help you in your development endeavors. On TI.com, a variety of references are provided to make the learning process as smooth as possible. Datasheets for each of the three major components in the DLP 2000 chipset, as well as the aforementioned Software Programmer's Guide, capture all of the technical information you need about how the chipset operates. On a system level, the EVM User's Guide and Reference Design provide support for your development and integration with the host processor. If you are trying to better understand the design considerations that demand your attention in a DLP project, consult our white papers and application notes to break down design trade-offs in an easy-to-digest format. Failing that, we are available to assist you with your questions on the E2E forums. When developing for a host processor, various libraries can be deployed to your system to speed up development and take advantage of powerful, mature code infrastructures. This, of course, is not limited to just the BeagleBone Black. Developers like you have already begun to experiment with the DLP 2000 using other host processors, such as the Raspberry Pi. We encourage you to experiment for yourself and see what the DLP 2000 EVM can do for you. Thank you for joining us in this TI.com training, and we hope you enjoy your experience using the DLP 2000 chipset in a smart home embedded project.